Okay, welcome folks, and thank you very much, Joe, for the introduction. So my talk here today is called Chasing Races, or how we did deterministic simulation testing in XTDB. So what's coming up? So first of all, we're going to talk about the value and cost of a test. We're going to talk about what we test specifically in XTDB and how. And spoiler alert, unlike every other testing talk ever, there is actually a bit of difference here to unit integration and system testing. And we're going to put a few more in there today, because I think you've all heard that talk before. Yeah, okay. We're going to talk about a little bit about the theory behind deterministic simulation testing. By the end of the talk, I'll be able to say it in one go. And what this looks like in Kotlin. So first off, the value and cost of the test. So this was a little thought exercise we did earlier on in the year. And we came up with a few factors that the value of a test is proportional to. So first of all, we said the false negative rate. So given that there is a bug in the system, how likely is it that this test is going to catch it? And not all tests are created equally here. And secondly, the probability of a bug in the code under test. Now, of course, being a developer, you'd say that there's always some probability of a bug, even with the most simple code, especially if it's before a coffee. But we know that not all code is created equal in this way as well. Thirdly, the impact. So there'll be some bugs, and like particularly on XT, we'll see that some bugs have much bigger impact than others. So for us, the absolute worst thing we can do is corrupt data on disk. And so any kind of bug that could have the potential to do that, we spend a lot more time testing those, and the value of those tests are much higher. Documentation value, of course. So the value when you're onboarding people onto the team or onboarding people into a new area of the code base. And I dare say that probably most people in this audience could think of a few other things that they would correlate with the value of the test. The cost. What's the cost proportional to? Well, first of all, obviously, time to write it. Obviously, this is getting cheaper in these days. I promised myself I wouldn't say AI in this talk, but yeah, that does tend to make these things a bit cheaper. The false positive rate. So given how many times the test fails, how many times of those are you actually interested in finding what the failure was? And wrapped up into that, there's sort of an intermittence of tests. So whether the test fails reliably every time, or whether it's due to some kind of a concurrent issue or non-determinism, whatever have you. Maintenance cost. So given that the code under test changes, how likely is it that you need to then update all the tests as soon as you make the slightest of changes to your code base? Again, I'm seeing a few sort of wry smiles there. You know the tests I'm talking about. And finally, sort of execution time and setup. So if you need to, for example, spin up an entire environment, which takes however long every time to run the test, then that's naturally a part of its cost. So what do we test on XT and how? So yeah, I promised this one wasn't going to be unit testing, integration testing, and system testing, and I've failed already on the first one. But I want to add a little bit of color to what's normally said here by saying that with our example-based unit testing, what we tend not to do is unit test every line of code under the sun. Again, the cost of the value of that test rather is relatively low. But what we do is we focus on areas that are what we call highly general. So for us, this is things like the bitemporal side of the system or the compaction side. Now, what these things are is where the code under test is actually dealing with a lot more cases than the code might initially suggest. So, for example, if you take in a SQL query, for example, we've got a planner there which takes in any arbitrary SQL query and needs to know how to plan it. And in that case, you've got one bit of code under test and many examples of what that code needs to do. Whereas if you've got code under test and your test is then sort of essentially reflecting what's in the code, that's less of a value. That's less of a value to us. We look particularly as well at complex outputs. So things like for the aforementioned query plan, when we plan that query out, one of the things that we're really interested in is, has this test made any changes to that plan? So how we test that is we actually spit out the output of those tests into files within the repository. And then anytime those tests fail, that's enough to give us a bit of a pause for thought and say, hang on a minute, should the change that I have made have caused that plan to change in any way? And so all we do essentially here is every time this test runs, it puts the new output in, and then we've got a git diff tool or similar, which will just say, right, here's the plan before, here's the plan afterwards. Were you expecting this? Similarly, we use that in the indexer as well. So when we're indexing transactions into XT, XT will then write some files out to disk. We've then got a way of representing that such that we can very, very quickly spot the difference between any two versions of that index. We talk as well about combinatorial explosions. So here again, XT, because it copes with a wide variety of sort of polymorphic data being put into it, data of any shape or size or any degree of nesting. This then the interactions between all of these different data types, when you've got, like, for example, a struct of lists of vectors of like ints, or even if it's a union type, like if you put an int in one day and put a float in the next, like the interactions of those, the interplay between them, has in the past actually caused us a decent amount of regressions. And so here we've very much gone on the property testing side of things. So we've got a generate. So think quick check if you're in Haskell, or test check if you're in Enclosure. Various code test, I think, does Cotest or Cotest, however you pronounce it, does that as well. So what this will do is generate any kind of any of these combinations of input data that we can then check certain properties against. Mainly these are, for like on the indexing side at least, mainly these are sort of round tripping tests. So we put this data into the database in this order. We expect to see something similar back out. Concurrent and distributed code. Well, this is very much sort of the deterministic simulation test, and that's what I'm going to be talking about in more detail after this slide. And finally, everything else, I say, is mostly example-based unit tests. So these are things where we've put quite a lot into making sure that the XT database can be spun up quickly in memory, in process, so that we can spin up a completely clean database, index the documents we need to, run the queries against it, and see what happens. These are good when you do get bug reports in as well, because it's very easy just to write a node that that reflects that bug, and then you can confirm it's not going to happen again. I did want to put a brief aside here about Allen intervals, because it loosely relates to what I was talking about with the highly general cases here, and I'm not sure how widespread this kind of formalism is. What Allen intervals say is that when you've got two periods, so when you've got a start and an end, and you've got two of them, they can interact in any one of 13 ways. And so what you'll find in a number of our tests is that we actually got tests for each of these cases, and named as such as well. So these are made up of 6 pairs. You can roughly see where the pairs are. Like, so before will pair up with after, meets and met by, starts finished by, finished started by, and then you've got one little outlier in the middle of equals, which is its own pair. But what this does is it gives us a language with which to talk about how these different periods overlap, and everything else actually, because overlaps is only one of them. You might think it's a bit weird coming into a deterministic simulation testing talk and saying don't do it, but that's essentially what this slide is saying, because it is, like, relative to all of the others, it is relatively complex, right? It does mean some changes to the code that you're trying to test, and so the advice here is very much like any risk, to avoid before you mitigate. And so there's a few things that you can do here, and the functional programmers in the room will no doubt recognize a few of them. So yeah, the immutability by default, avoid sharing mutable state. We also invest heavily in separating this pure code from side effects. And more recently, we've been moving a lot more of this code base to these communicating sequential processes or actors. So that's the example that we've got here on the right-hand side, where we do have state, for example, here. This is very much localized to this individual thread here, and so the thread is processing messages off a channel and updating the state. And because this isn't shared mutable state, we can trust this to be a lot safer than if that mutable state was shared. These then give you sort of a granularity at which to reason about this individual block of code and isolate it from the rest of the code base as well. Right, what's the problem we're trying to solve? Well, the main thing here is that concurrent code is non-deterministic. It's very much dependent on the timing of the exact run that you're doing, or in when this is actually in production, exactly what's going on at that time, who's connected to the database, who's querying it, what are they doing, are they writing, are they reading, is the data available on the node that you're querying? All of these kinds of things is very much sort of exactly timing dependent. And when you do this, there is this vast number of potential interleavings. I'll cover a bit more about what I mean by interleavings here in a moment. But perhaps most frustratingly, anything you would do to solve this issue makes it go away. Like you turn the logging up, it goes away because that fixes the timing issue. You put a debugger on, that absolutely fixes the timing issue. So this is one of the sort of more frustrating areas that we deal with. So solution to this is just run all of them. See if anything breaks. Thank you for coming to my talk. So let's talk about this happens before relation. So first bit of theory really behind the deterministic simulation testing, and this comes from Leslie Lamport's paper in 1978. It's one of those papers that's still relevant even today, maybe even more so than when it was first written. So I don't know. I don't know what they would have had around about that time, but it's certainly not the sort of level of distribution that we see today. But happens before is a formalism of how two processes can interact with each other. So what we say is that if two events are in the same thread, then A naturally happens before B. If A is the sending of the message by one process and B is the receiving of that message by a different process, then we know that event necessarily has to happen before that one. And there's a transitivity rule here where as well, which we say if A is before B and B is before Z in this case, then A is also happens before Z. But the key observation here from Lamport was that happens before is only a partial ordering. So it's not like numbers where you know whether any number is greater than or less than another number or equal to it. It's not necessarily the case that either A happens before B or B happens before A. And if that's not the case, then that's when we call these two events concurrent. And we need to consider what happens if they happen in either order. Now I'm sure you can imagine here the amount of pairs that we've got here, the amount of pairs of events that those combinations soon add up. I'm not going to say whether it's exponential or anything like that, because I'm not. Yeah, no. Let's avoid precise words like exponential there when I haven't looked it up. So DST, as I say, trying all the total orderings. So what do? Well, first of all, we choose an ordering and we run it. And once that ordering is run through, similar to property testing, we can then choose properties about that system. So properties here may well be so the round tripping. So the round tripping property that we had earlier, like any data I put in, I want to get out. It might be that all threads see the same thing under certain conditions. So like if I'm running a query twice, I expect to see the same results twice. More so in XT than other databases, obviously. But so yeah, if then that ordering does fail any of its properties, what we look for from deterministic simulation testing is that it allows the exact rerunning of exactly that situation, exactly that interleaving. And what we do then is that then gives us access to all these tools that we love using, like debuggers and logging and all of those kind of wonderful things. And because you know then that the bug is going to happen every time under that same ordering, that means we can use our usual tools. What are we looking for? Well, we're looking for low false positive and false negative rates, as I mentioned earlier in the value and cost of a test. So what this means is that we want to be testing the real code as much as possible. But we also don't want to have to change that real code hugely in order to get this kind of simulation working, because that kind of defeats the point of it as well. So we're looking to minimize the change to the code that we're doing. So I'll start off a little bit on how we do this in Kotlin, and first a little bit of the background. So apologies for the Kotlin folks in the room. There will be a few minor inaccuracies in this as I gloss over various things for slides. So if you can just, Kotlin folks, if you can contain yourself, that would be great. Right, calculate sum. So what we're doing here, the Clojurians will notice that the brackets are in a slightly different place. So what we're doing, we're taking two integers and we're summing them together. Now, of course, because this is an application that's going to scale, what we need to do with this, first of all, is we need to turn it into a microservice. So here's what we do if we want to delegate this important business logic out to a separate service somewhere else on the network. So here what I'm doing is I'm grabbing this URL, I'm interpolating the two parameters in, and we're grabbing the body back. You notice the first difference here is suspend. So what this is saying is that this function may, not guaranteed to, but may suspend and come back and execute a bit later. I'll take a bit of an aside, again, to talk about structure concurrency. So Kotlin has this great sort of great feature as part of its concurrency library called structure concurrency. And what I'd highly recommend going and having a look at this blog, Go statement considered harmful, where it essentially says that decades ago we figured out that unrestricted goto was a recipe for disaster in programming. And so what we did is we introduced structure that showed that told a compiler what this function could do, or most importantly, couldn't do. And the theory here is that Go is exactly the same, but with concurrent code rather than with sequential code as with goto. And so what the structure concurrency folks say is that we need to be very careful about what we do when we fork a process. We need to be very careful then about what's allowed to happen to those forks and ensure that they get joined then at some point in the future. So just out of interest, actually, so do we have Kotlin folks in the room who can correct me on some of this? Can I get show of hands of people who regularly use this kind of thing? Keep your hands up. Right, Max, there's your list of people for the talk for next year. Yeah, cool. So what does it do? Well, this is then a compiler transformation. And so you'll see this in Kotlin, you'll see this in JavaScript with async await, C#'s got it. You'll see in Clojure's core async with its Go macro. And they're all doing something along these lines. This, of course, is a gross simplification. But what we're doing is we're essentially turning this suspension function into a function that takes what we call a continuation. So what this continuation is saying is when you're actually done computing this value, then here's what I want to do with it. It's a callback. And those of you who've ever written JavaScript and ended up in callback hell, you'll probably recognize something like what the compiler tries to do for you down the bottom here as well. So what we're doing, we're passing it off to client.get, which is a suspend call as well. We're saying that when you get the result of this, then I want to resume my own continuation with the body of that response. That's enough theory. What does this allow us to do? Well, one of the affordances that Kotlin gives us here is this concept called the coroutine dispatcher. And this essentially allows you to intercept any of these suspension points that happen within your code here. So the important thing for us is this function here called dispatch, which is called any time that there is a block that requires executing. There's a few built-in dispatchers. There's a default one. There's one that you can run I/O on. If you do Android, then there's a UI thread in there as well. There's also a testing one as well. So Kotlin's coroutine tests gives you a test dispatcher. We've written another one for this deterministic simulation testing, which thankfully mostly fits onto one slide, so I can talk about it here. The idea is that as soon as we get a request in, we store this request in a list of potential jobs. We're running this all in one single thread so that we're dispatching onto the same thread that it comes into. And all this is doing is using a preceded random here, random object, to choose what block gets run next. So if we run this enough times, we get to see this kind of behavior. It chooses enough interleavings that we get bugs exposed within the program. So I mentioned earlier on about sort of how we might need to change the code under test in order to make it work this way. And aside from all the sort of usual FP best practices, one of the things that we have to do is every time that there's an observable side effect, we need to give the dispatcher a chance to reorder those two, chance to run them in both orders, if you like. So things like observable side effects, I mean the sort of the message passing between the various different actors, so whether that happens or not. But also for us, because we've got a shared object store, it's things like writing to that object store versus reading from it. And those kind of things we wrap up into a call that we want the dispatcher to get a chance to interleave and shuffle around. So for us, again, this isn't really any surprise to anyone who's done OO for any length of time. We extract this out into a driver interface for each of the components. But the key part here is that each of the functions on this driver is a suspend function. And given that the mock driver then uses these yields, what that does is that ensures a suspension within those functions. And that means that the code under test, the dispatcher will then run these in both orders. Time for a bit of a game of spot the bug. So here's one that we fixed with deterministic simulation testing. This is actually one that's upstream in the Apache Arrow Java library, so hence why it took us quite a while to find. I'll give you a clue, it's on the middle line. Okay, what we're doing here then, so this is a function that's incrementing a reference count for a little bit of memory. So we're doing a little bit of manual reference counting in Kotlin, which I know is not really what Kotlin's often used for. But say we're doing this reference counting. Now what happens here is that when the reference count hits 0, this resource is then free to be reclaimed, and the memory is free to be reused. But what we have here is a get and add, and we then check the result of check what the reference count was before, and if the reference count is 0 beforehand, then we throw in this case an illegal argument exception. But what it's done is it's left that increment on there. So let's say the reference count goes down to 0. I call retain on it. If it's 0, it's been reclaimed, but the reference count is now back up at 1. So anyone then trying to use that then thinks it's a valid reference. And bad things happen because the memory's already been reallocated somewhere else. So yeah, we raised this one upstream. That's upstream with Arrow Java. Why is that a race though? Because you'd think that would happen every time, right? That looks a fairly deterministic bug. It was a race for us because when we had 2 threads trying to increment the ref count, I say the ref count went to 0. One of the threads tried, got the exception, but then importantly, it evicted it from our cache. Its job was then to evict this memory from a cache. Before it did that, it was still in the cache. Another thread pulled it out. Its ref count was 1, and then T2 read the freed memory. Now, predictably, this didn't happen nearly as often as we'd like it to, and certainly when nobody was watching. I don't know if you've seen all the signs for the sort of the quantum untangling upstairs, but it very much felt like that. We could have checked the ref count first and then tried to increase it, but that's also a race as well. So what did we do? So I've got the dispatcher again here over on the right. But what our deterministic simulation tests look like in practice is something along the lines of what we've got on the left over here. So what we're doing is we're using our deterministic dispatcher. We're kicking off a few jobs. we are asserting properties about what the code's doing here. Crucially, we've got a yield in here such that we're giving the dispatcher more chance to get in there and interrupt what's going on. And then finally, once all of this is done, and again, the structured concurrency here will allow us to say, right, as of this await, everything within this block is done. Then we check the final results at the bottom here. And in this case, we wanted to check that all of the calls to this cache.get returned a valid buffer. What does it look like? It is IntelliJ. Don't worry about looking at the code itself. But what we see in practice here is that over 1,000 runs of this code, we end up with 9 failures out of 1,000 runs, which is a royal pain in any kind of normal testing. But what we've got here, if you see, is we've got a nice little seed value within the logs. So what can we do with that? Well, we grab the seed. Let's just chuck it up here in an annotation. Thank you, Dan. Bring the test run count down, and we'll run it again. And this time, you'll see it fails absolutely every time. And what we've also done here, as you'll see, is we've turned trace and debugging logging on, so we can see exactly the events that led to this particular failure. And at this point, probably what I'd do if I caught this in practice would be to turn the run count down to 1, stick the debugger on, and go and literally step through and see exactly what's happening in this case. So the fix, relatively small and isolated, thankfully. So we vendored this code into XT and made the change. But the change here is simply to turn this into a compare and set, which means that if the reference count is ever 0, we then don't make any change to the underlying atomic integer. So we put that change in, we run it again. Lo and behold, all 10 then succeed this time. So it's a chance for us to take the seed out, pop the test count back up to 1,000, and then we'll see this time that we got 1,000 passes. Very nice, happy days. All right, some closing thoughts. So I think anyone I've ever spoken to about this would say that I've talked about this way too much, but the FP practices are still as true as they ever were. Like this immutability by default, separating data from behavior, and particularly sort of separating pure from side effecting code as well. Like really brings down the sort of the granularity of things that you have to test in this way. Communicating sequential processes, CSP, has been a boon. And it says here, if you are going to have mutable state, you definitely don't have shared mutable state. But if you do have shared mutable state, then this DST is, as far as we can tell, the way to go. Thank you very much.